let's see. Here we go. All right, it's 2 after, and I think we're going to kick this one off, everyone. So,
Brian. Hi, Brian. How are you doing? Fantastic.
So, those of you who have joined, I'm Allison Baskey, Dean for the College of Science, and I am so thrilled to be able to introduce this year's awardee for the Richard W. Ames Distinguished Research Award, Professor Alan Krinik from the Department of Mathematics and Statistics. And as you can see there on his title slide, he will be talking about reflections on mathematical research and teaching. Now, normally I would be giving you this incredibly awesome certificate, Alan, and then they take pictures of us. And at some point we may do this, so pretend I've just handed you a beautiful certificate. and yes, there will be a check in the mail though too. So it's wonderful that with all of your years here at the institution that you are being recognized, not only for your research, but for the incredible footprint you've had on so many students. So we did get this email sent out earlier today, and I'll just read a few points from it, that you'll be discussing how you introduce students to mathematical research in a fun way by having them improve their problem-solving skills in counting and matrix properties. I just remembered linear algebra was not my favorite class, Alan, you know, so maybe you'll make it fun. Some examples that you'll show are puzzles that you'll just present and discuss. And after students hone their basic problem-solving skills, they can usually explore calculating probabilities of certain random events associated with Markov chains and processes. Beginning back in summer 2016, Professor Krinik did start a research group studying these topics. And in this group was composed of undergraduate students, graduates, and alumni, and that they have given over 15 talks to date at sectional and national conferences and other venues. Applications of this work and statistical data on the student research group are going to be shared by Professor Krinik. And he will talk about some of his past collaborative research. So with that, I don't want to take any more time from listening to what you've been doing and what you've been up to these last few years, Alan. And let's welcome our this year's Ames awardee, Professor Alan Krinik.
Allison, thank you so much for that wonderful introduction. And hi, everybody. I'm glad to see so many familiar faces. And let's get started. So the title is on the screen, Reflections on Mathematical Research and Teaching. And I'm very honored to be this year's Ames Award winner. And something interesting, I hope. This is Ralph Wolfley Ames, 2 pictures which I was able to find online. And there's a little information because I don't know that much about Dean Ames. I do now know that he was the dean of the at that time, School of Science from 1978 to 83. He started here as well as a professor, I assume assistant professor in 1961 in the Biological Sciences Department. And sadly, he served 5 years and passed away 3 years after being dean. So here's some actual pictures of how he looked. And one trivial fact is I actually met him. I guess he was going out of the deanship when I was coming in. So when in 1983, I was interviewing for my position. And of course, as part of the routine, I got to meet with the dean. So I actually met him in person. I might be the last Ames recipient to do that, okay? Unless there's someone else senior to me in the crowd. So anyway, that's a little bit of information about him. I'll start the talk, since research is what the award is about, talking about my graduate advisor, who is M.M. Rao. And M.M., this is a picture of him. It's 2 years ago. And we had a conference to honor him at UC Riverside, we being his students. There's a whole collection of us. And at that time, we were honoring his 90th birthday. So this is how he looked at 90. He gave a talk. Here's some of his talk. It was on screen, overhead projector, but still, at 90, I'd love to be doing that. And you can see he's quite animated. And well, up here, I say how I feel about him. He's my graduate advisor, a strong influence and an inspiration. He has hundreds of articles published, over 15 books, and many other books that he co-edited, monographs. And if you want to, if you ever feel a little like you're getting big for your britches, I guess I just got an ad for his most recent book. So now he's 92 currently, and they're advertising his most recent book. So that's really inspiring stuff. Here. After we honored him in 2019, at UC Riverside, Randy, myself, and Jenny, who are all co-editors on this book, thought we would put it into a monograph. And we're very excited to say that this monograph is supposed to be out this month. And so we're really excited. It's about him, but it's also about his students and about the good time we had when we had this conference when he was a young man of 90. Okay. Let me get into some puzzles. Here's an old puzzle, a traditional one. And you may have seen it before. You see before you 5 squares. And okay, I guess I got a little note about admitting somebody, but all right. There are 5 squares. The puzzle is to move 2 sides. I think it says down here, move 2 side segments to new locations, so that after these sides have been moved, so side is something between the 2 nodes, move 2 sides of what appears here to new positions to create exactly 4 squares instead of 5. Now, of course, you could just think, well, I'll just throw these 2 sides away and voila, I'll have 4 squares and that's it. No, you can't do that. You have to use all the lines, and they have to, go somewhere meaningful, connecting nodes. And so this is usually sort of a teaser of a puzzle. And why I include it is because a lot of what I'm talking about today is on counting. And I think this is not an easy puzzle if you haven't seen it before. So you might try it yourself. Try to find the 2 lines to create 4 squares. The 4 squares are the same size as the original squares. And it turns out that if you think about counting, it gives you a little insight how to solve the puzzle. I'll come back after a minute or 2. Here's a second puzzle. Also on counting, same squares, but this time we're thinking of them as a street map. And so here's home and here's school. And a student wants to walk along the street to get from home to school. And the question is simple. How many different ways are there to walk from home to school along this street map? Okay, I'm admitting people as I go along here. I'm getting little notes saying that I don't know if I'm supposed to be admitting them, but I guess I am a host. Okay, so, I guess I should say that students are assumed to walk only in south or east directions, because otherwise they could just go around the block all the time and never get to school. And we're assuming that they want to go to school, okay, not that they don't want to go to school. So now, of course, one way to do some counting problems is just to list them all. And that's a fine method as long as the list isn't too long, right? And so that's one way to do this, but I'd like to show you another way. Now let's see what's next. Oh, my solutions. Okay, so let me just go ahead and show you the solutions. So for the first puzzle, what you do is take the line that was here and move it over here, and take the line that was down here and put it as a side. And you see that there are 4 squares where there were 5. They're sort of oddball sides at first, but part of why I included the puzzle is counting helps. How does counting help? Well, if you counted the original from the original diagram, how many different line segments there are 16. And if they're going to be now in a configuration having 4 different squares, that means no side will be shared by 2 different squares. And that means the configuration you're seeking for from counting would have to be something like this one that you see before you, where you're only connected at the vertices or the nodes, and you don't have any common sides. I think counting actually helps you try to picture what you're trying to get, something like you actually see in front of you. The second puzzle. Well, here's a possible route where you could walk from school, the red lines, and that's one way to go. And instead of listing them all, I'm going to show you a method that would actually work not only in this case, but in any kind of street map that looks like this. Well, any kind's a little general, but most street maps. So here's what one can do. Starting at home, count the number of ways to walk to the nearest intersection. Well, to this intersection, there's only one way because you could only go east. Remember, you're only allowed to go east and south on the walk. So there's only one way to get here. And in fact, there's only one way to get to this intersection from home. You have to go 2 blocks east. So there's only one way to get here. So that's the idea. Label the intersections by how many ways there are to get there walking from home. Well, there's one way to get here. You have to go 1 block south. But here's where things get more interesting. To get to this intersection, you could have come from above, or you could have come from the west, I guess. And so there's 2 ways they could get here, either this way or this way. And that's the beginning of the idea. So if you want to know how many ways to get to this intersection, all you have to do is add these 2 numbers together. Similarly, if there's 2 ways to get here, there's only 2 ways to get here because you have to come from here. And you keep adding typically, if there are, well, there's only 1 preceding intersection, but if there are 2 preceding intersections, you add them to get the number of ways to get to the intersection. If you continue doing this, the answer turns out to be 11. By the way, for those who know Pascal's triangle, this is reminiscent of that, right? Where you add 2 entries to get to the third one. It's not exactly Pascal's triangle because you don't have all the entries on the rows, but it's close. Okay, let me now turn to puzzle 3. Oh, by the way, I like puzzles. I like them from a teaching point of view and learning. And in a talk like this, it's easier to convey ideas in a puzzle than to give a mathematical proof, which will be really long and probably hard to deliver. And so I'm hoping that maybe some of the ideas are going to get across on the puzzles. And with that in mind, I turn to puzzle 3, which is sort of the heart of what I'll be talking about later. This is the ballot box problem. So suppose you have a very small election. You just have 5 voters. And there are 2 candidates, and I named them Ursula and Doug. I named them Ursula and Doug because votes for Ursula will be going up and votes for Doug will be going down. So the letters help me remember which way the votes go. And suppose each voter has a 50-50 chance of voting for either of these 2 candidates, and let's assume there are no abstentions. So there's only 5 voters. They are voting they're choosing between these 2 people. And we're assuming that their vote will go to one of them. Suppose Ursula wins by 1 vote. Here's a way that could happen. So she could get the first vote because that's an up. From here they start 0-0. So she got the first vote, but Doug got the second. She got the third, Doug got the fourth. And then she wins it all by getting the fifth vote. Up is for Ursula, D is for down or Doug, either way you want to think of it. Up. And you can represent this path, this is called a lattice path, and you could represent it using ups and downs here. So this would be up, down, up, down, up. Okay. Here are 3 questions. Question 1, how many ways can Ursula win? I'm sorry, how many ways can Ursula win by exactly 1 vote? Which is what we pictured here. This is one of the ways she could win by 1 vote, but there are undoubtedly more, right? So it's like sort of counting the paths that we just did in puzzle 2 as well. Question 2 is related to 1. What's the probability that she wins by exactly 1 vote? And then the one that really sort of defines what's called the ballot box problem is question 3. If Ursula wins by exactly 1 vote, what's the chance that she was never behind during the counting? So this is, you know how things turned out. She won by 1 vote. But was it a nail biter where was she ahead and behind all the time? Or no, or was she always ahead from the start and never fell behind? That's what we're asking here. Okay, let me go through the solutions of this. Question 1, how many ways can Ursula win by 1 vote? Well, if we let script U be the number of U votes she gets, the number of ups, those are votes for her. And script D be the number of votes for Doug going down. Oh, I got to recompile here. I'm not on a PDF. Oh, I don't like that. I'll tell you why I'm not on the PDF in a moment. Let's just hope this works. Good. So I probably have to go a little slower in scrolling. I'm not on the PDF because the PDF changed some of the pictures. So I decided to risk just going off this, this file on Overleaf. Okay, so what do we have? We have these 2 equations. The number of ups and the number of downs are how many votes there are, which is 5. And U minus D is how much she wins by, which is 1. And if you solve the 2 equations by adding them together, you get the number of ups have to be 3 and the number of downs have to be 2. And that's pretty clear. If I just looked at the original, I have 3 ups and 2 downs. So any way in which she wins by 1, she'll have to have 3 of the votes and for her, and 2 could only be for Doug. So to answer question 1, how many ways, it comes down to how many ways can we place three U's among 5 places? And the answer of that turns out to be a combination number, 5 choose 3. And if you remember that from somewhere in your past, this is how you figure it out, and there are 10 different ways. And the nice thing about puzzles is the numbers are small, so you could actually list them all if you wanted to. Incidentally, for those who teach combinatorics, this is one of the areas where combinatorics confuses students. Why? Combinations count things where order is not important. Here, however, the order in which the votes are occurring is important. They're different lattice paths, and we're counting them using a combination number. So that's some of the challenges of teaching combinatorics. Sometimes orders being counted without you necessarily realizing it. That's an aside. Question 2, what's the probability that she actually wins by 1 vote? Well, we already have 10 ways in which she wins. And then the question is, how many ways could people have voted all together? Well, each person could vote either way, Doug or Ursula. And so there's 5 ways, 2 to the 5th would be the number of ways of different votes. So the answer is 10 30 seconds. And again, question one is sort of a setup for question two. If you want the probability, you need the number of ways something could happen by the total number of ways it could happen. Now let's look at three. If she wins by just one vote, what's the chance she was never behind during the count? Well, just for time's sake, I'll just tell you, you can count by enumeration. There are 5 ways that Ursula can fall behind and still win by one. One way, if she loses the first vote, if the first vote goes to Doug, she's already behind. So if D is in the first place, that will automatically be a path or a way that she falls behind. She fell behind on the first vote, in fact. The only other way that she could fall behind is to get the first vote and then lose the second and third vote to Doug, and then come back with a thrilling comeback with two upvotes at the end, okay? So there's only 5 ways she could be behind and still win by one. And we saw that there are 10 ways she can win by one. So there are 5 ways that she never falls behind if you just take the difference. And if you wanted the probability, which we did, and I didn't write it here, but it would be 5 out of 10, which is 1/2. So the answer to question 3 is 1 out of 2. There's a 50% chance that she was never behind during the count. Now here I solved the problem by listing it out. But what's behind the puzzle? What if n wasn't 5? What if n was big? Listing this all out might not be so easy. So that's in the back of our mind. Okay, so with this introduction to counting, that's it for the puzzles. And I hope they've helped a little bit. Let me talk about my grad students. Since I've been here a long time, my first grad student was 1989, Eero Sojak. And this is a list of all of my grad students. So I'm not here just to talk about research. I'm also here to talk about people. Okay, and I put some numbers. It's nice to see where these people go and what they've done. So the numbers next to their name tell you how many of my grad students actually wrote an article, or maybe co-wrote it with me or someone else, on their thesis topic. Most of them, well, some of them did not write things. Typically, if they wrote an article, it would be one. This gal is sort of special. She actually wrote 3 articles based on her master's thesis, and her name will come up later. And if you make a list and look at all of them, here are some of the statistics. There were 17 papers published from topics in their master's thesis. So that actually makes me really pleased to see that they've gone on and had enough interest to actually follow up on what they did in their master's thesis. 8 of the 29 people, and those are the ones that have asterisks next to their names, actually went on for their PhD. It's like a 270 batting average, which is not bad at baseball, okay? Anyway, and where they went to local schools mainly. 1 went to UCLA, 1 went to UCI, 2 went to UCR, 3 went to UCSB, which I might be tempted to too. That's a very scenic place. And 1 went to UC Davis. Where else did they go? Not all of them went on for PhDs. 3 of them are tenured faculty at local community colleges, Irvine Valley, Pasadena City College, and East LA. 3 of them became actuaries. Of the 3, I only know where 2 of them are, and those 2 are these 2. This is Iva, and she's doing very well. She was just named vice president of product and pricing of ICW Group, which is a huge firm in California. Ken is also doing very well. He's worked at Pacific Life Insurance. They both are actuary fellows, which really means they passed all their actuary exams, which is usually thought to be roughly equivalent to a PhD. 5 of the graduate students actually are teaching or have taught at Cal Poly Pomona. This includes our own Tracy McDonald, who's the director of our Learning Resource Center, and there she is. And just a few more notes. Matthew Doyle works for the NSA back on the East Coast. Carrie Mortensen, who wrote 3 articles related to her thesis, married and became Carrie Starbird. And here's a picture of her. And she's the Dean of Mathematics and Computer Science at PCC. Hey, I'm not saying I had a lot to do with any of this. I'm just saying it's fun to see where people go and to log their successes, right? If you look at some of the topics, starting around 94, reflections, reflecting paths in a single server queue, combinatorial solutions. Basically, what I'm trying to say is, starting around the mid-90s, I started to incorporate counting into investigations, and I'm an applied probabilist, so my main area is applied probability. Counting is a part of that, but those who really know how to count are called combinatorists. And I'm not a combinatorist, but I started to specialize in that and bring counting into the topics of these master's thesis. And that meant also counting got into the topics of my research as well. And just to say it in one word, I use counting to solve, counting and applied probability to solve linear systems of differential equations. So that's an overview of where my research started to take a turn to in the 90s. Okay. Let's go back to the math. Okay, so now it's a little more formal. These slides that you're seeing now are from research talks, but it's still the same topic. So I'm revisiting the ballot box problem. And so here it is. You got two people in an election, A and B, and A gets more votes than B. So A would be Ursula in this case. Compute the probability that A never falls behind B throughout the counting of the ballots. So here's the example, ballot box problem 1, or example 1. It's exactly the example I put in the puzzle. There are 5 voters, and A wins by 1. And you want to know the probability of this happening without being behind, which means without going below the x-axis. So now we're going to show a different solution method. And it has to do with the lattice paths. So lattice paths, we've already seen them. Here's another way for Ursula to win by 1. And she's never behind. Being behind would mean that she fell below the x-axis. So paths that are staying above the x-axis are called good ones. They're good for Ursula for sure. No drama in that election. On the other hand, if you fall behind, then you have to make a comeback to win by 1. And those are called bad paths. And we want to count both of these kinds of paths, but not just when n is 5. So we're trying to get some feel for how to do it. Here's a beautiful solution, which now is probably 140 years old. Okay, and let me see if I can describe it. So here's a bad path because it goes below the x-axis. It has to go bad somewhere. Where it goes bad, make it a red dot. And instead, it turns out to count the good or the bad paths themselves, or the good paths are very hard. So it's easier to count the bad paths, which is what we're concentrating on. And the reason it's easier to count the bad paths, excuse me, is you can do the following trick. Where it first goes bad, you can call it the first portion of that path. You can reflect it in this line here. So replace this part by this path. And what is going on now is that every bad path has a one-to-one correspondence with the path that's been reflected in the way that this shows. One-to-one correspondence, you can get technical and say what it means. It's one-to-one and onto, but instead of saying that, I'm just going to say two things are in one-to-one correspondence if they're the same number of elements in both sets. So since we wanted to count the bad paths, it's good enough to count the reflected paths because they're in correspondence. The correspondence takes a little while to convince yourself of. But I won't spend time on that. Well, okay, once you believe that there's many bad paths as there are reflected paths that look like this, then you can count the number of bad paths by counting these paths. And you can do that just like I did in the puzzle. You can say you're starting at -2 and you're ending at 1, and it's 5 steps. So the number of ups and downs must still equal 5. But this time, there must be more ups than downs. In fact, there has to be 3 more because you're starting at -2 and you're ending at 1. So the difference between the ups and the downs this time is 3. And so there's no restriction on these paths. So you can count it just like we did before. And the answer turns out to be the binomial coefficients 5, choose 4. And the solution, well, the solution is this. You want all the number of good paths because that means you choose always ahead over the total number of paths. That's all in this case. With good paths, as I've said, you can think of all paths minus the bad ones. That's the number of good ones. We know how to count all the paths. We did that in the puzzle. That was 5, choose 3. We know how to count the bad paths. We did that just the previous slide using the reflection principle. And then the difference of these two binomial coefficients, in this case, is 10 minus 5. And so you get the same answer that we got before. The chance that she doesn't fall behind, well, there are 5 good paths of that type out of possible 10. The good thing about this is it generalizes. So you can do it with higher n without listing things. And the solution is virtually the same, except you have bigger binomial coefficients. This is considered elegant. People in combinatorics love one-to-one correspondences because it allows you to count something you don't know how to count by relating it to something else that you do know how to count. Okay. There's a different way to do this, though, and that's what I want to talk about. This is elegant, and maybe sometimes something's too elegant and it doesn't generalize, okay? And I'm interested in generalizing this result past where we've started. And that's what my students have been doing. So we look at different paths again. Look at the paths that stay in this strip, such as this one. That's a good path. Never goes below the x-axis. And this is the tallest good path you could have. It can't go higher than this line. Why? Because there wouldn't be time to get back to J in 5 steps. So any good path would be in this strip. And you can think of the transitions going up and down to be a 50-50 proposition. And so you could form a matrix that shows the transitions. The states for the good paths would be 0, 1, 2, and 3. And this would be the transitions of going from one state to the other, because there's a 50-50 chance of anyone voting for one candidate or the other. If you then want to see what happens after 5 people vote, what you can do is basically take this matrix to the 5th power and come up with this entry. And this turns out to be the probability of going from 0 to 1 in 5 steps and making sure that they're good because you're in the good paths. So taking powers of a matrix is a different way of counting. Not as clever as the one-to-one correspondence way, but a little more down to earth. Then what do? Do the same, but for all paths, whether they're good or bad. Whether they're good or bad, they have to be in a strip like this. We already said this was the tallest good path you could have. This is the the lowest bad path you could have. Why? Because you can't go lower than this line and still get back in here in 5 steps. So the good paths would be all paths that take values in the red strip. Okay, take the matrix corresponding to that. It looks very much like the good path matrix, except there's a few more states. Take the 5th power of that matrix to count all the ways it could happen. This entry corresponds to going from 0 to 1 in 5 steps in the big strip, all paths. And then to get your answer, just take the ratio of those 2 probabilities. The chance of getting a good path in 5 steps was this. The chance of having some path go from 0 to 1, good or bad, was this. And the ratio is the same answer that we got, either by enumeration in the puzzle or by the reflection principle in the combinatoric style. So this is cool because, well, except for Allison, we're in the land of linear algebra, right? But you told me you didn't care for this much, but that's where we're going here. We're taking powers of matrices, okay? Same solution. Now, one reason we like it is we can generalize it. Suppose it's not a 50-50 proposition. Suppose Ursula, for example, the chance of voting for her is 1/3 and 1/2 for Doug, and there's an abstention. Somebody doesn't like either candidate, they just don't vote at all. So the same, you could assume these probabilities rather than the 1/2 one. And do the same process. So let's see how the process works. Form the good path matrix. This time it doesn't have all halves because we've assumed this kind of situation. Take the 5th power of it. This would be the probability of going from 0 to 1 in 5 steps, so just among the good paths. And then up the ante to all paths, which means you're on the bigger strip. Take the 5th power of that. This is the probability of going from 0 to 1 in the all path strip. Take the ratio of those 2 probabilities, and it turns out to be this, which is close to the 0.5 when there was a half chance, but it's not the same. And that brings up further questions. Why is this bigger than the other one? Should it be bigger than the other one? I can answer those questions later if we have time, but I don't think we will. But at least I point them out. Why do I like this? It's simple still. You're just taking powers of matrices. And I really like it because I don't know how to do it using the combinatoric solution. The elegant solution, the path counting, as far as I know, breaks down. So that means I know how to do it this way. I have a different way of doing it. We have a different way of doing it that we didn't have before. Okay, well, apologies to Allison. Okay, if you have a matrix, so now we switch gears and go into linear algebra. If you have an n by n matrix, which is known to have distinct eigenvalues, and if you don't know what eigenvalues are, it's hard for me to go much further, except to say that eigenvalues are very handy. They're sort of like the keys to the kingdom. If you know the eigenvalues, you know a lot about the matrix. Well, and this result says if you want to take, you have such a matrix where you have distinct eigenvalues. That's a restriction, by the way, but we're assuming that. Then you could take the kth power of the matrix by taking the powers of the eigenvalues. Eigenvalues are numbers times coefficients that are matrices. And if anyone's ever multiplied matrices together, the probability, it's no fun, at least by hand. It's much easier to take powers of numbers than it is to take powers of matrices. This result is old. That doesn't mean I knew it. In fact, I and my group of students in the research group didn't know it. We rediscovered it. And then we were kindly directed that this was a colleague, Ryan Schapowski, actually told me, pointed this out, this is an example of what's called Sylvester's eigenvalue expansion from the 1800s. Okay, so it's somewhat old. But it's what we need because we want to take powers of matrices, and why? Because of what I just showed you in the ballot box problem. And this gives us a nice way to do it. Here's an example for 2 by 2. And if you have a matrix that looks like this, then you can represent its kth power. These are its eigenvalues. One of the eigenvalues is 1. And these are the coefficient matrices. So this would be a way to take powers of a 2 by 2 matrix without taking powers of the matrix, but taking powers of its eigenvalues instead. Okay, I guess I should move along a little bit here. Oh, you can do it for the exponential matrix, which I won't get into. This is an example of that. If you know what that is, wonderful. Here's our problem in general with regard to the ballot box. You could have P's going up, Q's going down, and R are return probabilities. And we want to find powers of the matrix that has this form. That's what we were doing in the ballot box problem. And the research group that I've been on for about 5 years now came up with this solution with help from other people, including Hubertus von Bremen, who was very helpful, coming up with the expression for AS, which involves signs, which is pretty cool because if you're going from one state to another on this thing, you're alternating and going back and forth. It's sort of interesting that the expression for the matrix involves signs, which is also oscillating. Here's an example. If you wanted to go from 2 to 5 in this strip in 15 steps, you can get an expression for it in terms of eigenvalues. And that's what turns out to be the probability. And just as a final direction in this direction, I guess, if you go back to the ballot box problem we did, where we had 1/6 and 1/3 and 1/2, this is the eigenvalue solution. So instead of just taking the powers of the matrix manually, you can use this formula to get the appropriate entries. And if you take the appropriate ratio, you get the same answer that we got before. Okay, that concludes the math. What's left? Well, here's some things that I've been involved with. Research monographs. I've already showed you the one that's just coming out honoring Rao. But Randy and I did another one honoring Rao 20 years before that, essentially, or almost 20 years. And there have been other monographs. This one involves the lattice path combinatorics that I've been talking. And that came out in 2019. And there are others. So that's interesting. I have articles I could talk about, but I'm not going to spend time on that. What I'd rather do is talk about some of the collaborations with people. So one of the best collaborations that I could ever hope to have is with Randy Swift. We have 3 joint articles together. We co-edited 2 monographs. We co-organized many sessions at the JMM, Joint Math Meetings. On his own, not on his own, without me, rather, Swift also authored books on modeling and differential equations. And this is Randy. And also he was an Ames recipient 2011 and 12. So this has been a wonderful team productive effort that he and I have enjoyed. This picture he provided me, which I just love. This is Randy as well. And his colleague, well, now retired colleague, but former Professor Comte Rai. So this goes back to Randy's graduation from Cal Poly Pomona in 1985, I believe. Another collaboration was with Daniel Marcus. This is Dan. He was a professor here at Cal Poly Pomona. Unfortunately, he passed away around 2005. But before he did, he and I authored 3 joint articles together. And he was amazing. He was the individual author of books on differential equations, number fields, combinatorics, and graph theory. And he was a problem solver deluxe. So there's something in math called the Putnam exam, which is a really challenging exam. In fact, it's so challenging that the mode on the score is 0. So students usually get 0 on it. Dan used to proctor that exam. There are 12 problems. And when the exam was over, he knew how to do 6 of them on average, which was wonderful because he could share with the students how to do it. And then for fun, he'd go home and work on some of the other ones. So he was really unusual. It was a pleasure working with him as well. Here's some other people. Hubertus von Bremen, 2 joint articles with him, also a former Ames recipient. Jenny Switkus, where can I start? 1 joint article with her, co-edited the recent monograph as well. She's a multiple award-winning teacher. She's also an Ames recipient, 2015 and 16. And here's a picture of her talking at the RAL conference. I feel really lucky to have these colleagues. Very fortunate. There are a few more. Michael Green, of course, our former chair, among other things. I have a joint article with him, and we together with Randy co-edited a special issue of a journal. Ray Shiflett, who many of you may not even know, he was the former dean of the College of Science from 84 to 90. I have a joint article with him. More recently, Ivan Ventura, I've got a joint article with him. And Compta, though I didn't write an article with him, just a tremendous person, mentor, wonderful, influenced and encouraged scholarly activity, including being the co-editor of an in-house journal called the Cal Poly Scholar, which was really valuable when I was a young professor. And it was a great way to sort of do some research in-house, which wasn't as demanding, but it could really get you going. And it was very valuable and helpful for my earlier career. Last part, external joint collaborators. Sri Gopal Mohanty, 2 joint articles with him, a real lifelong friend. He's the founder of Lattice Path Combinatorics. So when I got interested in lattice path stuff, he was the guy. He offered these conferences that occurred every 3 or 4 years back then. And finally, he coaxed me into organizing the 8th Lattice Path Combinatorics Conference here at Cal Poly Pomona, which was a real pleasure. And that took place in August 2015. Another fruitful collaboration, Gerardo Rubino, who lives in France, 4 joint articles with him. Mark Bergen, who's Russian originally and has 2 PhDs, had 3 articles and a monograph with him. Dan Kalman, who's just an award-winning writer of mathematical articles. Fortunate to have 2 articles with him. And the last one I'll mention is an article with 2 really great researchers, Kristen Krakenthaler and Cyril Bandier. One is in Paris, the other is Austria. I've got a long article which came out of the Lattice Path Conference in 2015. Here's Mohanty. So in certain sense, I've been really, really fortunate to have 3 strong, influential Indian mathematicians. My advisor, M.M. Rao, Sri Gopal Mohanty is another one. He talks about his lattice path contributions here. And Compta Rai. So just incredibly fortunate. Here are some of the speakers that came to Cal Poly in 2015. There were over 30, and they gave talks in the big room in the library. I forgot what it is, 108 or something. That was a lot. That conference lasted 4 days. Here's a picture of Gopal and myself and another researcher, Higiri, at that conference. And I'm out of time, but I can't neglect what Allison first said originally. Since I stepped down as being chair in 2016, I've been involved in a Cal Poly Pomona research group, a wonderful group of students. This list is just some of them. So there's 34 of them. The group has been going on, meeting informally in a seminar fashion, which, by the way, is another thing I got from M.M. Rao. He used to meet with the students in a seminar fashion. So the students don't get any credit. in terms of units or in terms of grades, but they often end up talking at a conference because part of the point of the group is them to be exposed to going to conferences and seeing what's involved in that. And also writing an article. So the little key here, the star means they actually presented at a conference. Most of these people have never presented at all. This little mark means they're a co-author, and I'm smiling because so many of them have that little mark, and the reason is a recent paper I put all of these people on as co-authors. So I have a paper with 27 co-authors, which actually I didn't think it was going to work, but it did. There's more to say, but I think time is getting short. Oh, well, here are 6 of the people in the group. Some of them you may know. This is Jeremy Lin and Tui Lu. They're both students at UCI and the staff going on for their PhD in the staff department. This is David Beecher, Jeff Ye, who's also earned his master's here at Cal Poly. David Beecher is a double major physics and math. And Hiba Ayada, who got her bachelor's recently and currently is going on for the credential, but she's also eyeing graduate school. So many people to thank. So let me start with these people. Hiba, Jeremy, Beecher put together this talk. I cannot do this. They did the pictures, helped with the diagrams. I mean, I was there, of course, but they did the technical work, and I so owe them such a great thing for doing that. And as far as it goes, it's a good time to thank everyone. Definitely the department throughout the years has been a wonderful support for research, helping fund when we go to different places, and appreciate all the chairs. Appreciate the support from the College of Science as well. Throughout the years has really been terrific. And last but not least, I'll be in trouble if I don't mention my family. Okay. and I'm very, very appreciative of my wife and son who put up with my ongoing interest in research. Thank you all.
Thank you so much, Alan, for an amazing talk. Please join me in thanking him. I really enjoyed looking at puzzles, your research, and most of all, your collaboration that spanned across many years in the department and with your students. So I'm just here to host the Q&A session. And so I'll start reviewing the chat a little bit more closely to see if there's any thing that is there. But at this point, if you want to raise your digital hand or bring yourself off of mute, I'll acknowledge you. You can go ahead and ask any questions you have of Dr. Krinik.
I have
Go
two
for it,
questions.
Barrett. Yes.
Okay. My first question is actually mathematical, which is that I have some vague memory that maybe that work with the reflecting the sort of good path into a bad path and that kind of thing. Is that related to Catalan numbers? And then my second question, that you can answer them at the same time, is more of a comment, I guess. I just want to point out that not only have you collaborated with many of your colleagues, but you were really a leader in hiring many of your colleagues, including me. So thank you very much for that. And I wonder if you just wanted to say anything about the way that you've shaped the department by hiring so many of our wonderful colleagues.
Well, thank you. I take hiring very seriously, and I think I've made my life easier by the people that I was involved in hiring. And Barrett, you're there at the top of the list, but there's so many as well. So yeah, I think hiring is important, not only for that, but just to have a harmonious department, and I think we really have that. So I couldn't be more thrilled with how our department looks these days. And yes, it seems like Catalan numbers come into everything. so yes, it's about the good and bad paths too. Thank you for the questions.
So Alan, we'll save the chat for you. So Dan, could you make sure you do that? But there's just a lot of congratulations rolling in through the text in the chat there that we'll make sure that you're able to see. So I think my friend Brian Jersey. Brian, did you have a question there? I saw you were putting something in the chat where P equals Q equals 1/2. Was that a question that you wanted to ask Alan there?
Thanks, Michael. It's great to see everyone. I was just wondering about the case P equals Q equals 1/2 for those matrices. I think there might be an exception for that.
No, it still works. Is that what you're
Does it?
asking? Yeah,
Okay.
no, it still works. Except there's less need for it because you have the other combinatoric solution. But no, it still works. Brian, Brian, it's great to see you. Thank you for coming.
Oh, it is. It's my honor and congratulations, Alan.
Thank you. Great to see you after it's been a while. Missed you.
Alan, can I ask one inquisitive question? I was speaking with a chemistry colleague, and we were talking about building inquiry into our classrooms, and something that we discussed often is playing chess, working through various puzzles as you have given to be able to sharpen one's inquiry-based skills. Have you? What are your thoughts on that through the use of puzzles to be able to help, not only with problem solving as you've shown through the different exams, but just in general that span across all of our different majors?
Yeah, well, the different major part I probably would back off of because I'm not so sure how it would work in different departments. But in mathematics and statistics, I would say I'm a strong advocate of puzzles. First of all, they draw people in. They create interest. They don't need a lot of machinery. If they're well framed, and the good ones are, you can capture people's attention, and that's the first issue of teaching, right? Is make somebody interested in what you're talking about. Okay. And so a puzzle can do that. I will say puzzles could be threatening. So it has to be done in the correct way because people could, like the move 2 lines, I've had that done in class and people can't do it and they get frustrated and they think they can't stay in the class or something like this. So it has to be done in a very careful way so that you're not undercutting your purpose. The purpose is to draw people in and get them interested in math in a sort of simple, accessible way. The danger is that it could affect confidence if it's not done well.
Well stated, well stated. Well, we're at the top of the hour, and so please join me one more time in saying congratulations to Dr. Krinik and a well-deserved honor of being our Ames Research Award recipient. Thank you so much, Alan, and congratulations again to you. And thank you everyone for joining us, and have a wonderful rest of your day. We'll see you later. Thanks so much.
Thank you all.